Hey everybody, just a quick note on hybridization. In Chem 151, you covered the ideas of atomic orbitals, which you had your spherical s orbitals, you had your peanut shapes. Your peanut-shaped orbitals were p orbitals, and then you had the d, the double peanut. So they looked something like this. Then f's were too complicated to draw. We're going to focus on the s's, the p's, and the d's, because what we saw most recently in Vesper theory, valence shell electron pair repulsion, we didn't see s orbitals and p orbitals and d orbitals. What we saw were geometries like tetrahedral come out. So let's say we have something like CH4, where we have a central C atom. We've got 4 bonds coming off of it. 1, 2, 3, and 4 H's. So there's our CH4, 8 valence electrons just like it should have. If we count the number of electron domains around the C, I've got 1, 2, 3, 4 domains. Now remember, it doesn't matter if it's single, double, triple bond, a lone pair, all would represent 1 domain. So I have a total of 4 domains. A typical question is going to ask, what type of hybridization is on the central atom? Hybridization takes atomic orbitals and merges those atomic orbitals into uniform hybridized orbitals that end up reflecting the geometry that we have with Vesper theory. So if I have an s orbital, 3 p orbitals, and 2 d orbitals, let's consider this our playset that we start with. Then consider the number of domains that I've got in my molecule. In this case, CH4 has 4 domains. I'm going to take the s and 3 p's. That's 4 atomic orbitals that I'm going to take. 1 s and 3 p's for 4 atomic orbitals. When I hybridize those, it's just like taking different color Play-Doh and mashing it all up to get 4 uniform lumps of Play-Doh out of that. I'm going to get 4 sp3 orbitals out of this, or we could say that the central C atom is sp3 hybridized. If we had x times x, you'd say that this was x squared, in the same way that I have 3 p orbitals and they become p3. So sp3 hybridized for CH4. If we did the same thing for, say, this, acetylene, C2H2, and we wanted to know the hybridization on the indicated carbon. Well, we haven't indicated one yet, so let's pick the one that is on the right, even though it's really the same hybridization on each. We've got around that carbon 1, 2 domains. If we write out our tool set, we've got an S, we've got 3 P's, and 2 D's to work with, but I only need 2 of these because I only have 2 domains. This one and this one. So we would say around this carbon, I have sp hybridization. It's a nice little shortcut that works for any molecule. Now, let's work one from scratch all the way from the Lewis structure. Let's do Xe F2. Well, from Xe, xenon, I should have 8 valence electrons. From F, I've got 2 of them, and they each should have 7 valence electrons. You put that together, I get 14 plus 8 for a total of 22 valence electrons. Put your xenon at the center. I'm going to put an F coming off of the top and an F coming off of the bottom. And I'm going to start putting in my dots just to complete my octets. Where each little circle is representing an electron. Okay, so everything right now is satisfied with an octet, but I need 22 electrons, and on the structure right now I only have 20. So I need to put on 2 additional electrons. Those can go on the center. So now I've got my 22 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22. Yep. Okay, so that worked out, and the formal charges are perfectly fine if you check them. I've got a 0 on every atom, so that adds up to a 0 overall formal charge because the charge on XeF2 is 0. So I've got a good Lewis structure here. So how do we get to the hybridization? Well, the typical question again would be, what is the hybridization on the central atom? So we would be looking at xenon. And for xenon, we've got 1, 2, 3, 4, 5 domains around the central atom. If we look at our tool set, we have S, 3 Ps, and we'll just do 2 of the Ds, just leave them there. And we have 1, 2, 3, 4, 5 total domains. And it doesn't matter if they're bonding or non-bonding, just 5 total. So I'm going to pick 5 of my atomic orbitals, an S, 3 Ps, and a D. We're going to stop it right there. And that's all we're going to take. So I've got S, P3, D. sp3d is the hybridization of the xenon that's on the center. So I took 5 atomic orbitals, an S, 3 Ps, and a D, hybridized those, and off of my xenon I would have 5 sp3d orbitals coming off of my xenon that give it the shape that it has. And with 5 domains, its Vesper shape is going to be TBP for its electron geometry, but because it has 3 lone pairs, it would be linear for its molecular geometry.